Today we think of gravity as a force, one of the four primary forces in our universe. In the future, however, we may see it not just as a force of nature, but a tool for humanity to forge an awesome destiny. A couple months back, we explored how gravity could be used for spaceship propulsion, from modern methods like slingshots to the Oberth effect. As incredible as spaceships are, they're just one category of technology that could benefit from advanced control over gravity. Today, I thought we'd dive into some of the other possibilities. Everything from its role in terraforming planets to its impact on constructing megastructures, both in terms of the building process and the structures themselves. We'll also examine how gravity might enable us to settle giant planets or small moons, create or mine stars, manipulate time, fold space, and even wage wars. After all, gravity plays a crucial role in weapon performance, from deflecting impacts to shattering entire planets. But let's begin with a few spaceship applications, as gravity isn't just useful for moving your ship. Probably the best known use of gravity technology in science fiction is essentially to create artificial gravity on board ships where people live and work. Ironically, this is perhaps the least essential usage, as we can already simulate gravity through spin or rotation. While large rotating sections are necessary for artificial ecosystems, a habitation drum or ring doesn't need to take up much space on a ship. Plus, there is little reason not to rotate a ship. Spinning on its axis offers added protection since attacks from the sides won't hit the same spot repeatedly due to the rotation, making it harder for an enemy to pound away at a chink in your armor. The concept of artificial gravity in spaceships is more of a concession to practical filmmaking. After all, you can't simply turn off Earth's gravity during filming. Pre-CGI models of spaceships also required simpler, static designs, where moving parts were not feasible. However, artificial gravity has some unique advantages. For instance, with precise control, different areas of a ship could feature varying gravitational conditions. You might have high-gravity calisthenic gyms or low-gravity acrobatic arenas. Gravity levels could be adjusted in a single room as easily as adjusting a thermostat, a gravostat if you will, or even with the casual simplicity of a dimmer switch for lights. Beyond intensity, you could also control the direction of gravity, enabling rooms where every wall and the ceiling had gravity, maximizing usable space. This raises intriguing possibilities about how gravity might be generated. Would it create a large sphere of gravitational pull, akin to a massive object, where force diminishes with the square of distance? Or would it shape a gravitational field around the entire ship, pointing downward to the bottom of the vessel? If you found down an elevator shaft on such a ship, many of which might have dozens or even hundreds of decks, would you plummet to your death at high speed, or would gravity flicker on and off as you pass between floors, each generating its own field? If the former is true, then why limit ourselves to elevator shafts? We could repurpose them as gun barrels, where projectiles fall down the length of the tube, propelled by gravity instead of chemical explosions or electromagnetic linear motors. There was an enormous fictional ship called McCragg's Honor in the novel No No Fear by Dan Abnett, a Gloriana-class battleship described with various loose size estimates. A commonly accepted scale is about 20 miles long and 52 miles wide, or roughly 32 kilometers by 8 kilometers in each dimension. It's hard to estimate the number of decks, especially since the ship was built to accommodate genetically engineered giants over 2 meters tall. However, assuming an average deck height of 5 meters, the ship would have around 1,600 decks. There was a memorable scene where the ship's bridge is blown out into space, taking its master and commander with it. Everyone assumes he's dead, but thanks to his borderline demigod status from extreme genetic engineering, and the ship retaining a small atmosphere held in place by its artificial gravity, he managed to reach an airlock and re-enter the ship to continue the battle against treacherous invaders aboard his flagship. It's a fun novel, but some readers objected to the idea that the ship could retain any atmosphere through its own gravity. They are correct that even a solid metallic asteroid of that size wouldn't have enough gravity to hold an atmosphere, and ships are far less dense since they are mostly hollow. However, if the ship is equipped with an advanced artificial gravity system creating Earth-like gravity on its decks, it's not surprising this gravity might leak. Add in the ship's shields and the fact that it was parked in the planet's upper atmosphere at the time, and the scenario becomes more plausible. I've thought a lot about that scene over the years and even incorporated similar ideas into the juggernaut-scale ships for a video game project I worked on years ago, Hades 9. Though the game was sadly never completed, we still occasionally use footage from it. Our designs feature ships of a similar Gloriana-class scale with hundreds of thousands or even millions of crew members, set in a post-apocalyptic dystopia. These ships had main guns miles long, and their immense scale included cracks and crevices that spanned hundreds of meters wide and kilometers long. Entire unintentional ecosystems could develop in these spaces, sustained by air and water leaking from the ship and held in place by artificial gravity. Gun ports, in particular, were key areas where gravity manipulation was used to launch projectiles. These massive weapons relied on gravity capacitors to store and release energy, and the sheer size of the ships meant gun crews were like small towns, living near or even on the colossal guns themselves. This highlights something I always find fascinating when contemplating advanced technology, whether in serious discussions or science fiction: the secondary and unexpected effects of the technology. For instance, artificial gravity could be used not just for crew comfort, but also to accelerate projectiles. This might apply to giant ship-mounted weapons, vehicle-mounted guns, or even personal sidearms. As I recall, the Mass Effect video game franchise uses this concept for its weapons. If artificial gravity works for weapons, why not for body armor? Sci-fi often depicts anti-gravity suspensors or massive power armor, but rarely combines the two. Imagine a knight-like warrior encased in tons of metal, able to charge freely not because of pistons, servos, or synthetic muscle fibers, but because artificial gravity or reduced inertial mass makes the suit lighter and easier to move. Mass itself seems to have three distinct effects. It resists being pushed or pulled, inertial mass, it's put on by other masses, passive gravitational mass, and it exerts a pull on other masses, active gravitational mass. Normally, walking around in low gravity while wearing a massive spacesuit is exhausting because while the suit isn't heavy, its inertial mass still resists movement. Ships capable of manipulating inertial mass would have an easier time moving themselves. This idea is often implied in science fiction with artificial gravity systems. Otherwise, when a captain orders "take us to half impulse" or "take us to half light speed," we would expect the crew to be squished against the bulkheads by the sudden acceleration. For example, accelerating to half the speed of light in 1 second would require approximately 15 million Gs of acceleration, thousands of times more than would instantly kill a person under normal conditions. Just as importantly, if you can control gravity, you can change directions more easily without flinging the crew around. Otherwise, when two ships fly past each other at a decent fraction of light speed, firing broadsides, and one attempts to swing around for a second attack run, it would need to spend months accelerating at high speed to make that maneuver, leaving the crew glued to one wall of their ship. Gravity technologies also open up new defensive possibilities, in addition to applications in weapons and propulsion. For instance, a gravity beam, laser, or spotlight could serve as a tractor beam or a mechanism for launching fighters. It could also be used to manipulate large chunks of metal, positioning them several miles from your ship as a shield. These metal barriers could absorb damage, and if something does break through, it would scatter in the space between you and the shield, rather than ricocheting around inside your ship as it would if it pierced your armor. Something like this might work for defense on small-scale vehicles or body armor too. But that's not the only way gravity technology, or grav-tech, could enhance defense for ships, planets, or individuals. Imagine if you had a weak, fluctuating gravity field around you on the ground. Such a field could cause bullets aimed at you to miss their target. If it had an anti-gravity function, it might even push bullets aside or slow them down. Gravity also affects energy. Light blue shifts gains energy as it falls into a gravity well, just as objects like bullets speed up. An anti-gravity field could reverse this, redshifting light to weaker frequencies or slowing incoming projectiles. This assumes a simple push or pull gravity device. If a gravity field could push sideways, it might deflect objects entirely. Much like a far-distant electromagnet between Earth and the Sun can deflect charged particles better than Earth's own magnetic field, a long, focused gravity cone could potentially deflect incoming weapons fire, bullets, lasers, or even energy weapons, with minimal energy use. While these ideas are exciting for spaceships, they are equally applicable to space stations, habitats, planets, and stars. But before diving into those applications, we should ask, how does this gravity tech actually work? The answer, of course, is that we don't know, not just how it works, but even if it's possible. That's why we classify it as Clark-tech, a term derived from Arthur C. Clarke's famous quote, "Any sufficiently advanced technology is indistinguishable from magic." We recently did a comprehensive episode on Clark-techs, exploring technologies ranging from biological immortality, likely easier to achieve than faster light travel, despite sci-fi often suggesting otherwise, to those that seem plausible but have no clear developmental pathway, and others outright forbidden by known science. Gravity technology mostly falls in the category of plausible but currently inaccessible under known science. However, we do have some basic gravity-related technologies today. Spaceships use gravity for slingshot maneuvers and the Oberth effect. Spin gravity is employed in space habitats and even washing machines. And gravity powers mechanical systems like water wheels, pulleys, and counterweights. Somewhat ironically, while gravity was the first of the four fundamental forces to be discovered, and its basic behavior understood and utilized, it remains the least understood overall. The other three forces are electromagnetism and the strong and weak nuclear forces. Gravity is incredibly weak, trillions of times weaker than even the weakest of the other three, and appears to be strictly attractive, unlike the others, which have both attractive and repulsive components. In some ways, our incomplete understanding of gravity is precisely what keeps the door wide open for GravTech, as we simply don't yet know what can and can't be ruled out. Unlike the other fundamental forces, which have well-defined carrier particles like photons for electromagnetism and gluons for the strong nuclear force, gravity's carrier particle, the hypothetical graviton, remains undiscovered. While we hypothesize its existence, the graviton's compatibility with Einstein's theory of relativity is deeply problematic. For a more detailed discussion of these issues, see our string theory episode from last month, where we delve into the conflicts between quantum mechanics and general relativity. Gravity is the unseen architect of the cosmos, shaping planets, stars, and perhaps even the size and potential of alien life forms. And while at first we might think gravity limited the size of aliens, we also have reason to believe most aliens who could parallel us on other worlds would also be much bigger. In the Big Alien Theory, our monthly Nebula exclusive episode, we dive into the fascinating connection between the physics of size, gravity, and the mysteries of the Fermi paradox. Could the very forces that govern the universe also explain why we haven't encountered other intelligent species? Explore these captivating questions and more only on Nebula, the largest creator-owned streaming platform. Every episode of SFIA airs early and ad-free on Nebula, alongside a universe of exclusive content from myself and many other amazing creators, like Real Engineering, Real Science, The Science Asylum, Up and Atom, and more, including classes available on Nebula. Sign up at go.nebula.tv/IsaacArthur using the code IsaacArthur to get 40% off an annual plan, making it $3 a month. Nebula also offers lifetime memberships and gift options, so you can share incredible content like the Big Alien Theory with friends and family. Head over now to go.nebula.tv/IsaacArthur, and let's get back to uncovering the possibilities of gravity tech. That said, we've made some significant progress in understanding gravity. In the past decade, we conclusively detected gravitational waves, a prediction of general relativity. Observations suggest that these waves, generated by extreme binary sources like merging black holes, are not emitted uniformly in all directions. Instead, they vary in strength depending on the direction, implying that a directional gravity emitter could be possible. If true, this could allow us to project gravity in specific shapes, like cones rather than spheres, enabling applications like tractor beams or even launch corridors for spaceships departing planets. Manipulating gravity in a localized area of the atmosphere could also provide a straightforward path to weather control, a topic we will visit when discussing GravTech for planetary applications. Interestingly, almost every faster-than-light FTL travel concept under serious consideration today, such as warp drives or wormholes, relies on the existence of negative matter or negative energy. Personally, I'm skeptical about the existence of such phenomena, but if they do exist, they could provide a pathway to developing GravTech by enabling the creation or manipulation of gravitational fields using negative matter or energy. We also know that mass generates gravity, but that doesn't mean gravity can only be produced omnidirectionally or solely by mass. A deeper understanding of quantum gravity might reveal that gravitons do exist and can't be generated as easily and mundanely as we currently produce photons. If so, the possibilities for controlled directional gravitational fields and the revolutionary technologies they could unlock would be endless. Gravity control could significantly influence other technologies and the paths our civilization might take. For example, we often consider creating rotating habitats to house vast populations in space using rotation to simulate gravity. If artificial gravity eliminates that need, habitats could be designed flatter and simpler. Furthermore, structures could be built much larger without requiring supermaterials or an energy-intensive active support systems. Interestingly, gravity control also allows for smaller-scale innovation. Moons or dwarf planets, which struggle with low gravity, could have their gravity enhanced comfortably, at least within bases and settlements. Terraforming could be far more practical, enabling adjustments to gravity on heavy planets, maintaining atmospheres and oceans on smaller celestial bodies like moons or asteroids, or even supporting life on asteroids themselves. The concept of terraforming, by the way, originates from Jack Williamson's short story Collision Orbit. In that story, the term refers to a small asteroid that someone claimed and equipped with an artificial gravity field, making it capable of retaining an atmosphere and providing Earth-like gravity. Whether such grav tech is viable depends not only on how complex it is, but also on whether it requires energy to operate. Mass naturally generates gravity with no energy cost. Of course, energy is involved when objects move up or down in a gravitational field. But the field itself is a constant. Similarly, spin gravity doesn't inherently consume energy once established. A hollow cylinder spinning in space will keep spinning indefinitely, aside from minor frictional losses. Even in a vacuum, there are some particles to bump into. If artificial gravity operates like these systems, it could be practical for large-scale continuous use. However, suppose it required energy to maintain, say 1 watt per square foot, or about 10 watts per square meter. In that case, something like the International Space Station would need around a 5 kilowatt generator or solar panel to maintain gravity. While that's not insignificant, it suggests you could feasibly limit artificial gravity to specific areas, like workspaces or sleeping quarters, or activated only when people are present, much like we do with lighting. The power requirement is purely arbitrary. I chose it because it's comparable to the energy used for bright room lighting. The actual requirement could be much higher or lower. Using that figure, a USS Enterprise-scale spaceship might need to burn through a megawatt to maintain its gravity, possibly more if it must supply gravity to each of its dozens of decks individually. We also don't know how such gravity would diminish with distance. Does it remain uniform and simply stop working beyond a few meters, or does it follow an inverse or inverse square law relative to the distance from the gravity plate? If it diminishes with distance, would that mean your head experiences noticeably less gravity than your feet? At a planetary scale, generating gravity at 10 watts per square meter will consume about 2 to 3% of the sunlight hitting the planet, assuming Earth-like illumination and a 100% conversion rate, turning photons directly into gravitons with no loss to heat. For quarter asteroids, heat loss might not be a concern, as any sunlight not reflected would simply warm the rock. It might also be perfect for a planet like Venus, where we get a bit too much sunlight and the gravity is a bit low, and there will be a lot more Venus-sized planets than Earth-sized ones, and even more at 80% Earth's gravity. It's just the nature of how matter tends to clump, more smaller items than bigger ones, though more mass in the bigger ones than all the smaller ones combined. It's worth noting that a 10-kilometer wide asteroid with Earth-like gravity would not automatically retain an atmosphere like Earth's. We've previously discussed the idea of creating artificial black holes of arbitrary sizes for purposes like generating gravity. If your gravity force falls off inverse square with distance, then a 10-kilometer wide object has only a quarter of the gravity 10 kilometers up at the top of its main atmosphere layer, which isn't holding things in well at that point. Plus, atmospheres go up a lot higher than that. An inverse rather than inverse square force might do much better, and that might be possible with artificial gravity. In the absence of that tech, we could do this with a small artificial black hole. By placing a micro black hole at the core of an asteroid, moon, or megastructure, you could generate gravity using abundant mass, such as hydrogen or helium, rather than valuable rocks and metals. Dark matter, which is even more abundant and less useful for construction, could serve even better if you could direct it into artificial black holes. If gravity manipulation becomes possible, it might enable interaction with dark matter, one of the few ways we might reliably manipulate it. mass might not even be necessary to generate gravity. Alternatively, if artificial gravity requires power to operate, the energy could be used to compress dark matter or excess hydrogen and helium into artificial black holes. This is a point we'll return to later. Energy does generate gravity too, so it might be that you need to dump that much energy in, the equivalent of the appropriate mass energy, untold trillions of tons, to make it work, though that would really limit the value of such technologies. However, an asteroid with Earth-like gravity, created via a micro-black hole at its core, would likely still need a transparent spherical shell to retain its atmosphere. The escape velocity of a rock with Earth-like gravity is far lower than Earth's, and the gravity would sharply decrease just a few kilometers above the surface. A shell would help maintain the atmosphere. Fortunately, we already have materials that are as strong as steel yet transparent, making such a shell feasible. Many plants might wrap themselves in transparent shells or construct a honeycomb of giant domes for similar purposes. These structures could also house artificial magnetospheres to deflect ionizing particles that strip away planetary atmospheres. As mentioned, you could lower the gravity on more massive planets, but maybe more importantly, you would use this to extract material for use elsewhere, planetary mining or harvesting. High gravity makes extracting and transporting materials from such worlds energy intensive and dangerous, as machinery and human operators must contend with crushing forces. By using artificial gravity to reduce or counteract the planet's natural gravity in specific mining zones, equipment could operate more efficiently and workers could move safely and easily. Furthermore, artificial gravity systems could create controlled environments that stabilize loose soils or manage the flow of excavated materials, reducing the risk of collapse or equipment wear. For particularly dense or high-pressure environments, artificial gravity could even assist in lifting mined materials off the planet's surface, either by counteracting gravity during launches or funneling extracted resources through specialized gravity-assisted transport systems. This technology would open access to the vast mineral wealth of massive planets that are currently impractical to mine. Artificial gravity opens up fascinating landscaping possibilities. Instead of simply using it to hold loose soil in place, it could be used to run water uphill, creating spectacular mile-high waterfalls as it flows back down. It could also enable innovative architecture such as spiral hallways where you walk upside down or buildings with sidewalks running down the sides, adorned with gardens and trees jutting outward. Imagine looped gardens on pathways that invert as you walk, or even entire floating islands suspended in the sky. On a grander scale, artificial gravity could allow for immense, hollow megastructures filled with air, spanning millions of kilometers. Within these vast spaces, floating islands of rock and water could drift by as serene oases or lush gardens, redefining the concept of landscapes and habitats. This raises concerns about energy conservation and production. If I can make water run uphill, I'm either expending energy to move it or violating the law of conservation of energy. Otherwise, I could create a perpetual motion machine by having the water flow uphill only to fall back down a waterfall onto a water wheel, continuously generating energy without any input. On the one hand, this is perfectly fine. As we discussed before, while energy is locally conserved under known processes, there is no strong reason to believe it is conserved in all cases. The Big Bang and the continuous expansion of the universe is driven by dark energy seemingly coming from nowhere. Both suggest that energy conservation is not a hard and fast rule in this universe. It might be conserved within some broader reality from which our universe emerged, but even if that's the case, it doesn't preclude us from generating energy or gravity by similar mechanisms. Dark energy itself behaves in ways that are intriguingly opposite to gravity in some respects. Furthermore, under string theory, which we discussed last month, gravity's weakness compared to other forces is theorized to stem from being spread out over extra dimensions and realities. If any force seems plausible to violate energy conservation through artificial generation, gravity would likely be the prime candidate. Artificial gravity could also play a pivotal role in cosmic engineering. It might enable reversing Hubble expansion, creating floated pockets of spacetime to hide civilizations, or even generating slow time fields, similar to how time slows near massive bodies, ones where time was slowed or even suspended, though we might better call them hibernation fields, where time stops or nearly does. This would be distinct from suspension fields, which might be better suited for floating objects. On the architectural front, gravity beams could serve as safety nets, catching people who fall or jump from tall buildings or bridges, potentially a life-saving innovation and an exciting alternative to bungee jumping. You could also presumably have buildings hanging in the sky, or new options like upside-down pyramid buildings or cylinders of reverse gravity that let you fall from the ground up to some city in the sky. Much depends on how much energy is required to maintain these effects. If GravTech allows for violations of energy conservation, this becomes less of a concern. Gravity control, however, also opens up new methods of energy generation, one of which is artificial fusion. For instance, if we could increase the gravity of our Sun, the fusion rate would rise significantly. Fusion rates scale faster than the cube of the gravitational force, so doubling the Sun's gravity could result in an 8-fold or greater increase in its fusion rate and brightness. Artificial gravity could transform gas giants and brown dwarfs into stars by inducing sufficient gravitational compression to ignite nuclear fusion in their cores. Gas giants like Jupiter and brown dwarfs, which are often called failed stars, lack the mass required to trigger sustained fusion naturally. By artificially increasing their gravity, we could compress their hydrogen-rich cores to the pressures and temperatures necessary for fusion to begin. This process might be gradual, using gravity fields to simulate the effects of additional mass without needing to add physical material. Such engineered stars could serve as new energy sources, light up dark regions of space, or support terraforming efforts on nearby moons and planets. Additionally, these artificial stars might be customized to burn at lower intensities or for longer durations, creating stable environments for humans or alien habitats. Artificial gravity could also be useful for small-scale commercial fusion. Creating a gravity field the size of a basketball with 1 billion times normal gravity might be no more challenging than generating artificial gravity for a spaceship. Additionally, it offers valuable applications for managing oversized stars. For instance, we've discussed mining stars, known as starlifting, by using their emitted energy to extract matter from their massive gravity wells. This process could be used to extend a star's lifetime by removing fusion byproducts, cycling in fresh hydrogen, or even preventing large stars from going supernova by decreasing their mass. Artificial gravity might significantly simplify these processes, making them more efficient and practical. Supernovae are critical for producing the heavier elements that planets are made from, but we could likely replicate those effects more efficiently by using gravity. For example, we could imagine supercolliders that create new elements powered by gravity instead of electromagnetism. Supernovae also give us black holes, which can be incredibly useful, especially if artificial gravity allows us to create very small ones. We've explored using black holes for power generation and other advanced technologies in several episodes. Check out our discussions on Kugelblitz black holes, black hole tech and quasar cannons, colonizing black holes, and weaponizing black holes for more on these fascinating possibilities. But while using artificial gravity to make black holes could be amazingly useful, it is a reminder that black holes have a lot of uses, including warping space and time. And if we're contemplating anti-gravity, not just gravity, that warping might not be limited to squishing up, folding, or slowing space-time, but also to expanding or speeding it up. This could open the doors to applications like fast time bubbles and reverse time bubbles, along with wormholes that might open up to other places and times in the cosmos. So we see a lot of awesome gravity technology options exist, and doubtless far more we haven't thought of yet, showing us how useful gravity might be. Not that it isn't already pretty handy. Gravity is the awesome force that holds us all together, and it might be that in the future it's what lets us easily travel around the present or even the past.